Now let's start our digital image processing and analysis lecture. So let's define first what digital image processing is. Digital image processing can be defined as the act of examining and interpreting images. So in our first lecture, we have gained a first-hand clue about the basic properties of electromagnetic energy and its interaction with Earth object, its interaction with atmospheric particle. All of these properties will influence the remote sensing signal that is going to be captured in the form of digital image. Once we obtain that digital image, what we are expected to do is to process it and to extract some type of information from it. So what is all about digital image processing is you examine, you interpret the image with the aid of computer. Without computer, there is no digital image processing. The word digital means it is related to computer. So what do we do when we do digital image processing? We do image correction, we do image enhancement, we do feature extraction, information extraction, such as land cover types and the like. So why do we care about digital image processing? Because most remotely sensed data are digital image data. Therefore, data processing in remote sensing is dominantly treated as digital image processing. So what do you think is the advantage and the disadvantage of undertaking digital image processing? We know about its advantage. It is cost effective for large area. For small area, maybe you don't need to do digital image processing. You can do it by visual interpretation. And it is cost effective when you do the same analysis for again and again. So for repetitive interpretation, it is cost effective. And if you have a standard image format, it is cost effective. There are image formats that are very difficult to interpret, to process, to open. You need a very specific, knowledge. But if you have an image data format, which is very much standard, is a commonly used format for such as .TIF format, .img format, .jpg format. These are standard image formats. Then if an image is stored in such type of formats, it is cost effective. And you can obtain consistent result through digital image processing. Since you do digital image processing with the aid of computer, with the aid of algorithms, so you can do consistent analysis and you can expect consistent result. So, and another issue is simultaneous interpretation of several channels. So we have learned in chapter 2, there are different satellite programs with different bands. For example, if we take Landsat image, and if we take a sensor, thematic mapper sensor, it has 7 bands, 7 channels. So you might have asked, how can we interpret all these 7 channels, 7 bands at the same time? So one advantage of digital processing is you can interpret those several channels at a time. It gives you the multi-spectral view of a certain landscape. Complex interpretation of algorithms is possible. Speed is an advantage, and you can explore alternatives through digital image processing. So that's why we are learning. So there are the common steps in digital image processing, and what are the categories of digital image processing? What are the steps and the categories involved in digital image processing? There are 4 categories that need to be known. The first one is preprocessing. The second one is image enhancement. The third one is image transformation. The fourth one is image classification and analysis. So mind you, the second and the third steps are optional steps. They can be omitted. So you might be able to carry out your operation only pre-processing and image classification and analysis. But sometimes you may need to do image enhancement and transformation. So, but this is a standard for categories of image processing functions. You have to do pre-processing first. What is pre-processing? The name itself tells you something. Pre-processing, okay? These are operations that you can carry out before the main analysis and information extraction, okay? Pre-processing. Once you do those pre-processing, you go on to image enhancement and transformation and classification analysis. So we will start with image processing. Pre-processing functions are operations required prior to the main data analysis and extraction of information to correct image data for distortion, for errors. Okay. So we have obtained a clue about when an electromagnetic energy emanates from the source, that is a solar, that is a sun. So the solar energy propagates through the atmosphere, and it interacts with Earth, it interacts with atmospheric particles. So there are some energies that are going to be attenuated. There are some energies that are going to be scattered, absorbed. There are some portion of energy that are very much, capable of reaching the surface of the Earth. These wavelength ranges are called what? Atmospheric windows. So remote sensing operates in atmospheric windows. So the error that is going to be registered, that is going to be captured together with the essential information about Earth's object, you will find these two information captured in one image. So what you need to do is to separate this error, this distortion, from the required information. So that is what pre-processing is. So pre-processing involves again three categories. In pre-processing, you can do geometric correction. If you have an error related to geometric distortion. And the second category is you can do radiometric correction. That means you are expected to calibrate the data radiometrically. That means you have to adjust the digital values for the effect of a hazy atmosphere. Okay? So the third category is noise removal. So these are the three types of pre-processing categories. Before you jump into image classification, you need to do geometric correction, radiometric correction, and noise removal. What is really geometric correction is? Raw digital images usually contain both systematic and non-systematic errors. Systematic distortions are errors that can be corrected using data from platform ephemeris and knowledge of internal sensor distortion. What is platform ephemeris? This is a data provided by the satellite data provider. Okay? Since the error is systematic, so it can be modeled easily, it can be captured easily, so it can be corrected mathematically. So when you download the satellite data from data providers such as Landsat data providers, you will be given a metadata. That metadata contains how you can do your systematic distortion. Okay, how you can do your correction of systematic error. The best example of systematic distortion is skew distortion. So when an image, when the satellite revolves from north to south, the Earth rotates eastward. This eastward rotation relative to the satellite revolution, it creates skew distortion. The best example is this one. You see this, it is some kind of tilted view of the satellite image. Okay, this is a skewed distortion, skewed view of a satellite image. This is because of skew distortion, because of the eastward rotation of the Earth beneath the satellite during imaging. Okay, so this can be corrected by the data provider. So you cannot do anything in order to correct this skew distortion. You will be provided by making some kind of mathematical correction to make it like this. Okay, but you have to be aware that whenever you get an image like this, it doesn't mean that it is distorted, but it is corrected. Okay, this is the satellite path that you can see. Okay, so you need to be aware. The other one that we can do something about it is non-systematic distortion. Okay, these are errors that cannot be corrected with acceptable without a sufficient collection of ground control points. Okay, so the data receiver, the analyst like you or the expert, once he receives the data from the satellite data provider, he can do some kind of error correction about non-systematic errors. So he is expected to collect some geographical ground control points and correct the data. So this involves geometry correction. Okay, so nowadays most satellite data providers usually give you a satellite data by correcting the geometric distortion already. So you don't need to do any geometry correction whenever you have the satellite data, especially when you use Landsat satellite program. Okay, but previously or 10 years ago, the data were downloaded and you were expected to do geometry corrections and the like. But now when you download the satellite image, it's already geometrically corrected. But you may find some areas which are not geometrically corrected. In such cases, you may do your non-systematic correction, non-systematic error corrections. So this is how the satellite captures the data. Okay, so this is the angle of beam. So this is a sensor. So when the Earth rotates eastward like this, the satellite revolves from north to south. Okay, this kind of rotation creates this kind of view. Okay, but when you do geometric correction, you have to collect sufficient ground control points. What are ground control points? Ground control points are those areas, those clearly discernible areas or points that can be identified in both the satellite image that you are going to correct and on the data that is already corrected. Okay, this is the image that you are going to collect and correct, and this is the image that you are collecting ground control points. Okay, so relating ground control points from the correct map to the uncorrected map is called geometric registration process. So this registration process may be two types: image to map coordinate geometry correction option, or image to image geometry correction. When you collect ground control points from map, it is called image to map geometry correction. When you are collecting GCPs from satellite image, from a corrected satellite image to uncorrected satellite image, then this type of geometry correction is called image-to-image geometry correction. When you do your geometry correction, there is a very important process that is called resampling operation. Resampling operation. Resampling process, the resampling operation calculates the new pixel value from the original pixel value in the uncorrected image. There are three common methods of resampling. It is nearest neighbor, bilinear interpolation, and cubic convolution. So these are the three types of resampling techniques by which you can use during your geometry correction. Okay, but what is nearest neighbor resampling is? Nearest neighbor resampling uses the digital value from the pixel in the original image which is nearest to the new pixel location. For example, take a look at this image. This was the uncorrected image. When you correct it, it's going to have this kind of corrected position. When it gets a corrected position, the corrected image doesn't have a pixel value. You have to assign a pixel value using nearest neighbor. If you are using nearest neighbor resampling technique, it uses the nearest pixel value to this new position. And as you can see from here, what do you think is the nearest pixel value from the old one? The one that is found in the black dot is the nearest value. So this value is going to be assigned to this plus pixel value. So the nearest pixel value will be assigned to the new location. Okay, now let's take this another example. This is a corrected image, but this is an original image. When you correct this original image, it takes this position in the corrected image. Okay, but it doesn't have any pixel value. It is empty image. You have to assign pixel values to every pixel of the corrected image. How do you do that? If you are using nearest neighbor, you are taking the nearest pixel value. For example, for this pixel to assign a value, so where can you get a value if you are using nearest neighbor? The pixel value that is found very near to this pixel is the one that is shaded at the back, will be assigned to this pixel. If you are using bilinear interpolation, it takes the weighted average of 4 pixels that's found nearest. For example, if you are going to assign this value, it takes 1 pixel, 2, 3, 4 pixel average and will be assigned to this pixel value. Okay, this averaging process alters the original pixel value because in the corrected image it takes the average of 4 nearest pixel. Okay, this averaging process will cause some smoothing of the data. Okay, this is one. The third resampling operation is cubic convolution. This takes a weighted average of a block of 16 pixels that's found near to this pixel. So it is 4 by 4. The average of 16 pixels will be assigned to this one. So this result is completely a new pixel value. So it produces images which have a much sharper appearance because of the averaging process. The blocky appearance of the nearest neighbor method will be avoided. So mind you, in these 3 types of resampling methods, the first one is nearest neighbor. It doesn't involve changing the original pixel value, and hence it brings blocky appearance of an image. The second one and the third one, cubic convolution and bilinear interpolation, since they involve averaging of the nearest pixel, then they cause smoothing of the image. So it gives smoothie appearance. So it gives a much sharper appearance. Okay, so the second pre-processing operation is radiometric correction. Radiometric correction. What is radiometric? The word radiometric usually is related with digital number that is recorded in the pixel. Digital number is the amount of reflected energy, okay, in that specific place or location. So when you say radiometric correction, you are correcting the digital number that is recorded in a satellite image. That digital number may involve some kind of error. That error may be caused by different reasons. Maybe due to, due to other unimportant information that is coming from the outside environment, okay, other than the object of our interest. So the satellite sensor will record a mixture of two kinds of brightness in any condition. One is the brightness that is coming from the reflectance from the Earth's surface, the brightness that are of interest for remote sensing. That means the reflected signal that is coming from the object. Okay, this is one thing. The second thing is the brightness of the atmosphere itself. This is the effect of scattering. Okay, scattering means, you remember this thing in our second lecture. That is when the solar energy propagates through the atmosphere, it forms some kind of interaction. Two basic interactions are scattering and absorption. The scattering will cause, radiometric error. So you have to be able to remove this brightness of the atmosphere, which is the effect of scattering, from the required one. In remote sensing, what we are interested in is to get only the brightness of the reflected signal, okay? So in doing radiometric correction, what we do is removing this effect of scattering and making the image pure, making the image free of this kind of error. So once we do that, we can go on our analysis. Okay, there are several procedures to do radiometric correction. It's called conversion to at sensors radiance, conversion to top of atmospheric reflectance, and the like. So this is beyond the scope of your subject, so you may neglect this step. Okay, but the second digital image processing operation that can be done on an image is image enhancement. Okay, the original image that may be captured by the satellite sensor may not be visible to human eyes, and it may not be convenient to interpretation, and it may not be very convenient for information extraction and land cover classification and analysis. So you may need sometimes to enhance the original image. How can you enhance your image? By using three procedures: linear contrast stretch, histogram equalization, and edge enhancement. So most of the time, edge enhancement we use when we need enhancement of specific features such as roads, rivers, and the like. So otherwise, we don't need edge enhancement. Edge enhancement is more applicable to geological applications such as lineament extraction. Okay. So what does linear contrast stretch is? If this is the histogram of the original satellite image that is full of error and which is not enhanced, this is the original image. This is a histogram. A histogram is what? It is a graph which shows you the number of occurrence of a digital value versus the digital number. For example, the frequently occurring digital number ranges from 84 digital number up to 153. There are unused spaces from 0 up to 84 and from 153 up to 255. Maybe because there are unused spaces in the brightness value, the image may not be visible, may not be enhanced. But when we stretch to these unused spaces linearly, this is called linear contrast stretch, the visibility of the image will be enhanced. Okay. But when we use sometimes histogram equalization, the frequently occurring, this range of values of a digital number are frequently occurring brightness value. So you give much emphasis when you stretch, when you enhance it, okay? You give less emphasis to the less occurring brightness value, but you give much space to the frequently occurring brightness values. This is called histogram equalization, linear contrast stretch. So these are image enhancement procedures. The third digital image processing category is image transformation. Image transformation is required to generate new image, the so-called new image, from the original two or more sources which highlight particular features or properties of interest better than the original input image. Okay? For example, the most common example of image transformation is NDVI. We have learned how you can calculate normalized difference vegetation index. Normalized difference vegetation index is a transformed image. You calculate it from the original image, from band 1, from band 3 and band 4 if it is Landsat TM. Okay? We used normalized difference vegetation index because this index will highlight a particular feature of interest, such as what? Vegetation can be highlighted by transforming the original bands, band 4 and band 3, into a new image so that we are able to identify vegetated features from water body and from soil. Another example is principal components of a multispectral image using principal component analysis. When you do principal component analysis on multispectral image, it converts into very limited number of principal components. When you have 7 bands, the principal component analysis will convert that 7 bands into 2 or 3 very relevant principal components. In doing so, you are transforming into a new image that is very useful. We use this type of image transformation in order to highlight particular feature or in order to remove unwanted information and to reduce the dimensionality of the data. Okay? So now we are coming into a very important aspect of digital image processing, that is image classification and analysis. As I told you earlier, the image enhancement and the image transformation can be omitted. Once you finish your image pre-processing function, you can directly jump into image classification analysis, and this is very important. Okay? So what is image classification? Image classification, it is an operation which classifies each individual pixel based on spectral information. Okay? So the process of image classification is a process which converts spectral information into spectral pattern recognition. Okay? So in image classification, we assign all pixels in an image to a particular class. Okay? For example, converting the original image, this is original image, which is digital number, which is composed of digital number. So changing this digital number into class, into teams, is called classification. So the whole objective of this topic is converting this digital number into classes. So that's why it's called classification. So information, class, and spectral class. So thematic classes are these ones. Spectral classes are based on spectral signature of pixels. So there are the couple of procedures. The process of image classification typically involves 5 steps. Selection and preparation of the remote sensing image. You have to select your type of remote sensing image. This is very much related to the second chapter that we learned in our lecture 2, which is about the different satellite programs. The different satellite programs will give you information about the different remote sensing image. For example, we have seen Landsat with different sensors. You have to be able to select the appropriate remote sensing image from even Landsat. Do I use Landsat TM image? Do I use ETM image? Do I use OLI image, Landsat 8? Or shall I jump into a Spot program satellite? Or shall I use European Space Agency satellite programs image? Or what shall I use? These are the kind of things that needs to be discussed first before you go to your image classification. So preparation of remote sensing image means what? It is pre-processing. Then you define the clusters in the feature space. Feature space is what? It is a cluster. It's a scatter plot of a digital number of two bands, okay? Band 4, band 3, for example. If you make a scatter plot of two bands, okay, you can create a kind of this kind of cloud, okay? There are specific features which can be identified if you click this, and there's certain features which can be identified if you click this, So all of the digital numbers do have meaning, okay? Once you do those creation of feature space, you go to selection of classification algorithm. What type of classification algorithm shall I use? And you run the actual classification, you validate the result, okay? Then you finish your classification. But in selecting your classification algorithm, there are specific procedures that needs to be known, okay? Classification procedure can be categorized based on the type of learning, based on the assumption of data distribution, based on the number of output you need. Based on the type of learning, classification can be divided into supervised learning, unsupervised learning. For example, the type of learning means what? Supervised means what? You are classifying your image based on supervised classification algorithm means you have to train the computer in order to classify a certain digital numbers. Without the help of the expert, the computer cannot do any operation in supervised classification. The name supervised tells you that the computer is being helped by the analyst, okay, by telling this is water body, this is grassland, this is agricultural land, and the like. But when you use unsupervised classification, the analyst or the expert is not supervising the classification process, but rather your computer will take the whole responsibility of categorizing those pixels into classes. Okay, that's why it is unsupervised. So during unsupervised classification, the computer uses, some kind of statistical operation, statistical clustering of pixels to create classes. Okay, that is unsupervised classification, and based on the number of output you need, classification algorithm can be hard classification algorithms, soft classification algorithms. So hard classification sometimes means crisp classification algorithm. Soft means fuzzy classification algorithms. What does hard mean in your classification output? When you are using a hard classification algorithms, then the number of output you are expecting is what? Either 1 or 0, either presence or absence. So presence-absence map is the best example of hard classification, okay? But in soft classification, there is no presence and absence, but there are a range of classification outputs between presence and absence, okay? Between 0 and 1. range of the, in this case it is called fuzzy classification output. Okay, the membership of a certain pixel to a certain class cannot easily be defined in soft classification, because the percentage, the membership of a certain pixel to forest may be 0.1, 0.2, 0.3, 0.5, 0.1, or finally it may become 1. Okay, if you have a classification like this, then the classification output is fuzzy output. But based on the data distribution, you may have parametric data distribution, you may have non-parametric data distribution. You use only there are a couple of classification algorithms that you are forced to use for parametric and for non-parametric data distribution. Sometimes, for example, maximum likelihood classification algorithm can only be applied on a data which is parametric. Okay, what does parametric data distribution and non-parametric data distribution? Parametric data distribution means the data distribution has got a bell-shaped curve like this. Okay, so if the data has got a bell-shaped curve, then the distribution is parametric, which means if the data has normally distributed data, okay, if it is normally distributed data, then it is parametric, and it is not normally distributed, then it is non-parametric. When your data is non-parametric, you are forced to use parallel piped classification algorithms or minimum distance domain classification algorithms. These are supervised, unsupervised, and supervised class. So I have already explained this to you. This is a procedure, and the advantages of unsupervised classification. It's obvious. The unsupervised classification is not controlled by the analyst, so you don't need to go to the area that you are analyzing, so no extensive prior knowledge of the area is required. And the other advantage is opportunity of human error is minimal. And the other advantage is the classes are often much more uniform in respect to spectral composition, since the computer uses its statistical algorithms to create cluster, then you get much more uniform classes. And another advantage is unique classes are recognized as distinct units. If that unique class is created, the computer puts it as a distinct class. This is an advantage. Okay, the disadvantages and limitations. Unsupervised classification identifies spectrally homogeneous class within the data, and these classes do not necessarily correspond to the informational categories that area of interest to the analyst. Yeah, what you obtain from the result of unsupervised classification may not necessarily correspond to the real world. Okay, the best example for this is when you are expected to map, for example, wheat and barley, wheat and barley. So both of them, both of them will reflect similarly, and hence the spectral grouping will form a similar class, okay, as if they are one. So this type of result may not correspond to the real world situation. So in order to avoid this, what you need to do is to go to the field and check and take ground control points and train against the computer and tell that this is wheat and this is barley. This is you are now mixing, or you are making a hybrid of supervised and unsupervised classification. So, and another advantage is analyst has very limited or no control over the menu of the classes. Okay, the menu is highly controlled by the classification algorithm in unsupervised. And this is supervised classification. And there are a couple of procedures for supervised classification. You need to select training areas, you generate signature, and you classify it. There are methods of supervised classification algorithm. Here you are. For example, under supervised classification, what are the different algorithms that are involved? Under unsupervised, you have ISO data classification algorithm and k-means classification algorithms. And under supervised classification, you have maximum likelihood classification, Mahalanobis distance classification algorithm, minimum distance to mean classification, neural network classification, parallel pipe classification algorithm. The most commonly used one is the maximum likelihood classification algorithm, and the most common in unsupervised classification is ISO data classification algorithm.